Hello all. In this video we're going to talk about some variations on the basic uninformed search algorithms that we were looking at before, so breadth first search and depth first search. And then we're going to look at an extension of this from the realm where all costs have to be equal and we just have to count the steps to problems where each action may have its own cost, and we need to take that into account when we do the search if we want to find the optimal solution. So we're going to look at a variation on Dijkstra's algorithm, which it's called various things in different places, but I'm going to refer to it as lowest cost first, or LCF, because that matches the textbook that I'm currently using. All right, so let's first just talk a little bit about some other variations. So we talked about the efficiency of breadth first search and depth first search, their pluses and minuses. Breadth first search will find a solution if one exists, and it will find the optimal solution, but it uses a lot of memory to store the queue that it keeps its fringe set in. And depth first search, when we talked about it, if the search space is finite, it's guaranteed to find a solution. It may not find the optimal one, but it is much more space efficient. It's much more efficient in terms of space usage than breadth first search. So some of these variations are intended to address the problems that we have with especially depth first search, but also potentially with breadth first search as well. So the first option that is on our list is called depth limited search. So, and I mentioned this already in the earlier video. If we aren't sure that our space, if our search space, our state space is so big or potentially infinite, we don't really want depth first search plunging off into the wilderness and never coming back, we can use depth limited search. So with depth limited search, you just set a cap on how far depth first search is allowed to go. Maybe it's only allowed to go 4 steps away from the start. And if it doesn't find a solution, it isn't going to take that 5th step. It's instead going to backtrack and look for other solutions that are closer at hand. This is a nice variation, especially if you have a sense of about how many steps there should be to a solution. It's particularly good for spaces, as we've mentioned before, where you have lots of different solutions. So finding one within, say, 4 or 5 steps, or 10 or 12 steps, or whatever it might happen to be, is a reasonable expectation. So it does avoid this wandering off problem. It does keep the costs limited because there's only so far we're going to go. But if we're wrong about how far away the goal is, this one will fail to find the goal. So remember that completeness property we talked about before. Depth limited search without any possibility to extend is not complete. It could fail to find a solution that exists because it just doesn't look far enough. So iterative deepening is a fancier algorithm. And on the surface, it seems like it's just addressing that last point. So it just repeatedly performs depth limited search, gradually increasing the depth. So it'll try searching up to X steps away, and if that doesn't work, then it'll redo the search, but go further. Maybe it does to 2X or something like that. So it does repeated depth limited search, and it increases the depth limit by some fixed amount. There are variations on this algorithm that change how much you increase the depth limit. So it really does vary depending on the problem. There are some things that are really interesting about this, because this algorithm, if we go up by 1 at a time, so we first do iterative deepening that looks 1 step ahead, and then we do it that looks 2 steps ahead, and then we go 3 steps ahead, even though it's doing depth first search for each of those, it is guaranteed to find an optimal solution. Now, if you skip multiple steps, that decreases. You're not going to necessarily find an optimal solution if you go from 5 steps to 10 steps to 15. But if we're going up by 1 each time, it will in fact find the optimal path. And it acts like breadth first search in general. If you think about how I'm describing the search, it has that breadth first search flavor to it. However, it uses depth first search type of memory because it is in fact doing depth first search. There's a cost to that, which is that it will have to recompute the same intermediate paths over and over. So it'll do all the paths that are one away, generate all those steps, then it's going to throw them away. And at the next step, it's going to generate all the steps from the beginning to 2 steps away. That will involve regenerating all of the one-step states, but then it'll throw them away again. And then on the third round, it generates all of the 1 step and 2 steps again. So you get this sort of recreation of states over and over and over again for this algorithm. So trade-offs are the heart of algorithms. When would you use this? Well, when you really don't want to have the memory penalty that breadth first search puts on you. So you need to save memory. And it isn't expensive to generate those partial states, those intermediate states. So it's not such a big deal that you generate them over and over and throw them away. You have to decide for a given problem whether that's the case or whether maybe this isn't the right choice. There's another search variant that's also an interesting one called bidirectional search. This is most appropriate when you have a small number, one solution state or a small number of solution states, because the idea is that you can start your search in the forward direction from your start state, and you can also start searching from the goal state backwards towards the start. This means you need to be able to generate predecessors of a state. So you need to know, like undoing an action, what states could have led you to the goal, and then what states could have led you to that. So it has a little more sophisticated information that you need to keep track of. But it's possible that this could be more effective. One particular part of the space might bog down if you're searching forward, but when you're searching backward, you don't hit those nasty labyrinth areas where it can't make very good progress. So you run the 2 searches at the same time and you stop when they meet. Because when they meet, it's likely to be the most optimal solution that you're going to find. This is an interesting one to me because of this question of what happens if you have multiple goals. And as I said, if you have a small set of goals, you could potentially search backwards from all of them and see which one you get to first. This starts making me think that this would be an interesting algorithm to imagine using some sort of parallelism on, so that you're actually searching it at the exact same time using different processors. All right, so these are just some variations. None of these is going to address the fundamental problem of what if actions don't have the same cost. Breadth first search and depth first search will not produce an optimal solution if we have to take into account weights, costs that are variable. There are existing algorithms that handle this. Dijkstra's is the classic one that most people know. It handles weighted graphs, and therefore it could handle a state space where the actions are weighted by how much they cost. There are issues with the usual formulation of Dijkstra's algorithm in that it assumes that you have the whole graph. If you think about that algorithm, if you go look it up, what you'll see is that it says to make tables with a row for every node in the graph, and where you keep certain information in that table. And then those tables get updated dynamically as the program is running. It actually has kind of a dynamic programming feel to it in that sense. Well, when we're talking about some of the state spaces we're looking at, we don't necessarily have the whole graph. So we need a variation on Dijkstra's that gets at the heart of what it's doing, but that doesn't need those tables kept because we don't necessarily have all that information or want to build the table for the whole state space. So lowest cost first, or least cost first, is an algorithm that is essentially making the same decisions as Dijkstra's, but it's building the state space on the fly as a search tree instead of working with tables that represent the whole graph. So it's designed to work for state spaces where actions have different costs. If you give it a state space where all actions have the same cost, it behaves like breadth first search. That's what it devolves into if you don't have a difference in cost. This introduces a new concept that we need to pay attention to: path cost. So before, we just counted how many steps there were in the path, and that was how we could tell what the best solution was. Here, we need to keep track of the cost of the edges from the beginning, from the start state to whatever state we are currently at. We have to add those up. And that means an extra bit of information that the algorithm has to keep track of. All right, so least cost first or lowest cost first. What does that mean? It means when we have our fringe set, we are going to look at the path costs for each of the elements in that fringe set. And we will choose the fringe element, the frontier element, that has the lowest cost every time. This is what Dijkstra's algorithm does as well. It looks at the path cost and it always chooses the one with the lowest cost. Our assumption here is that all costs are positive, that there are no actions that have a net negative cost, that gain us a benefit and don't cost us anything. You can't use this algorithm if you have that situation, so you need something more complicated in that case as well. But for us right now, if all costs are positive, then this algorithm will be guaranteed to give us a really good solution. So one of the things to realize is that because we're basing this on the cost so far, this is not like depth first search, where we sort of can almost imagine, like with depth first search, someone walking through a maze and then backtracking and taking another path. This will jump around throughout the entire state space. It'll explore in one direction and then jump and explore in another direction, wherever the lowest cost happens to be. It just bounces around to keep evaluating lowest costs. All right, this is a key point, and of course the subpoints are broken over the page, so I'm going to just shift this up. When we first reach a state in lowest cost first, we actually don't know that we've reached it by the least expensive route. We only know something is a least expensive route when we choose it out of our data structure and we visit it for the final time and generate its neighbors. That means we can't do that early goal exit that we could do with breadth first search, where as soon as we generated a goal state, we were happy and we could stop. Just because we generate a goal state doesn't mean that the path we're on is actually the lowest cost. It could be that we will discover some other way to get to the state that is of lower cost. So we do a late goal test. We wait until something comes out of our queue, and then we check to see whether it's the goal or not. We also have to be prepared because of that we might see a state multiple times. Generally speaking, you do not add the state to our data structure more than once. It's only one time in the fringe set, only one occurrence in the frontier set. So what we do is we have to be prepared to discard one and keep another when we have a second path to a particular intermediate state. So it's kind of like if you have two different paths you could go to get to a particular state from the start, we might visit one first and then find the second. When we have more than one, we just keep the better one and throw out the other, no matter which was first or second. All right, one of the things I skipped over here is that I should go back to is that lowest cost search uses a priority queue. So it's going to store all of the frontier elements in order by their priorities, and it will always choose the one that has the lowest cost. So it's going to do, if you know your data structures, it's going to do a min heap to represent this. All right, let's take a look at the pseudocode. So I'm flipping back over to my pseudocode document. This is actually the pseudocode for breadth first search. I wanted to remind you of what it looks like. You know, we have set up the frontier and the explored state sets and queues. We set up we have the check at the beginning to see if the start is a goal. We have our loop. We grab a current element, we generate its children, and then we process the children. Now I'm going to scroll down to show you what lowest cost or least cost first looks like, because I can't quite see all of it. I'm just missing the last line that returns a failure if the search fails. This still looks a lot like breadth first search. We still have a start state as our input. We check to see if it's a goal. Here, we're just changing out on line 3. We're changing out the queue to be a priority queue. But we still have the explored set. And in fact, the explored set is more important here than it is in breadth first search. We're going to add the start state to the frontier. Generally speaking, the initial cost is 0. There are some cases that we're going to look at where the initial cost might not be 0. But often this is the case that we start with a path cost of 0. We're at the starting location. So we haven't done anything yet. We have our while loop, while the frontier is not empty. We're going to grab the current lowest cost state from the queue and then remove it from the frontier. And notice that now the goal test is here. Now as it's coming out of the priority queue, we check to see if it's a goal state. If it is, then we return. We just stop the loop. We found the path, we found the goal, so we're done with our search. If it's not a goal state, notice that here, as we pull it out of the priority queue, that's when we mark it as explored. That's when we're finished with it. It's not until it comes out of the queue. When we add things to the queue, we don't typically mark them as anything. All right, but if we're exploring this node and it's not a goal state, then we generate its children, just as before. We're going to loop over the children. We have to calculate the cost now, which we maybe didn't have to do before. So we take cur state's cost and we add to it the cost to get from the current state to its child, to its neighbor. And that's going to be our new path cost. And here we have 2 cases that we have to handle. If we have never seen this child before, this state before, it's not in the explored set and it's not in the frontier set, then we do the same thing that we did before. We add it to the frontier. And it has the cost that we've calculated. But if the child is in the frontier already, there are 2 possibilities. One possibility is that the child is in the frontier, but it's the better solution. In that case, the new child that we've generated with a new path cost, we want to throw that one away. We've found another route that gets us to that, but it takes longer. On the other hand, if the child is in the frontier, but it has a higher cost than our new path, what that means is our first way that we found to get to that state, it's not the best. We've found a shortcut, and we want to replace the one with the other. So that's what we do right here. We replace the version of the child with the current version of the child. Notice another thing. If the child was in the explored set, it will not be in the frontier set because we take it out of the frontier before we add it to the explored set. And neither of these will apply. Once something has been explored, we're done with it. We know the optimal path to get to that, and we never have to look at it again. All right, so I've said this, I've beaten around the bush a little maybe, but I'll say it outright right here. This algorithm will produce the optimal path. Much like breadth first search, it's guaranteed to be optimal. We're not going to prove it. You can go and look up proofs that Dijkstra's algorithm produces the optimal path. It does. this is just a variation on Dijkstra's, and so the same proof actually applies here. All right, the last thing I want to do is to go over an example, but I think I'm going to wait and do that in a second video. So in this video, we took a look at variations on breadth first and depth first search, and this variation is the biggest step because it's really moving us into a new set of problems where we can have weights. We still do have the constraint that our weights, the cost, has to be positive. We can't really model situations where costs might be positive or negative. We need a more elaborate algorithm for that. But for now, this allows us to solve a lot more problems than we could solve with just breadth first or depth first search alone, or with any of those variants that we talked about early on. In the next video, I will take a look at an example of a problem space, and we'll walk through what happens with that example, and then we'll see if that helps to illuminate exactly how this works. I will see you very soon.